everyone. So it's a pleasure to be here. I think this is like my third or fourth time in this workshop. It's getting better every time, so I'm really happy to be here. All right, so today I'm going to talk about SELFIE. This is a self-supervised reconstruction for fast dynamic MRI. All right, so let's see if it runs. There you go. These are just my financial disclosures. All right, so in dynamic MRI, so here we're actually acquiring a video, right? This is a time series of images where the video is actually showing physiological information that goes beyond the anatomical information in static images. So popular examples are like this movie here showing cardiac motion, and this has become a clinical standard now to assess cardiac function. So another one that's getting also a lot of popularity now is to image tumor motion and also the neighborhood of the motion. And this can be used to guide procedures like radiotherapy or surgery. So here we see the tumors. This is a pancreatic tumor, and then the organs at risk, like the stomach and duodenum, and also the small bowel. So another one, which is also very popular, actually is a workhorse in cancer imaging, is a contrast-enhanced imaging where we're actually injecting a contrast agent, and then we need to take a video with like super fast temporal resolution to see how this contrast is moving through the different parts of the body. And in this particular, this is showing like here breast cancer. So you see, I mean, that this contrast agent will shorten the T1. So in a T1 weighted image, you will see, these parts are getting brighter. So this is the tumor, and actually you can also run like an analysis and quantify this, and to get like a tumor perfusion map. For example, K-trans that is like measuring the tumor permeability, and with that you can see actually how heterogeneous is the tumor. So how aggressive is the tumor, and for example, in parts with higher perfusion, well, you're gonna get some more aggressiveness of the tumor, and parts with lower perfusion, probably like hypoxic regions. So anyway, so tons of new information in these dynamic images. So now the issue is where MRI is relatively slow compared to other modalities, there is a real need for speed in dynamic MRI. And that is, if we're fast, we can accommodate high temporal resolution, high spatial resolution, and also high volumetric coverage. So these are competing requirements. And as we already saw in this session today, so the way to do that, so the way to accelerate acquisition is to acquire less case space data per frame, in this case for dynamic imaging. And so one acquisition that we really love, and Dan already mentioned GRASP, and so we developed that a few years ago when I was at NYU. So it's using these golden angle radial acquisitions, and so which are separated by the golden angle. So and the golden angle is basically just like, at least in 2D, is 111.25 degrees. And in plain English, what we're trying to do here is the next spoke will try to fill the largest gap in case space. And if we do that, so we can actually get uniform coverage of case space for every number in the Fibonacci sequence, like 2, 3, 5, 8, 13, 21, 34, etc. All right, and so if we are now going to move to 3D, since we need to get some volumetric information, so what we usually do is we use a stack of stars, where so the KZ dimension will be Cartesian, and then KY and KX is going to be radial, right? So we select the first angle, we go through the KZ dimension, and then golden angle rotation, we get the second angle, so on and so forth, and then we get our stack of stars, okay? All right, so let's now talk about some properties that we're going to use to actually self-supervise these type of acquisitions. So one of the nicest properties is that we can get this flexible case space reconstruction or sorting a long time. So once we complete this acquisition, it's a continuous acquisition, we acquire like hundreds of spokes. So they can be actually sorted in different ways. So like low temporal resolution, you're gonna put more spokes per frame. With high temporal resolution, fewer spokes per frame. And as I said before, if the number of spokes in each frame is one of these numbers in the Fibonacci sequence, you're gonna get a uniform coverage of K-space, okay? All right, so the other nice property is that we have this high undersampling capability, which is from radial imaging. That's, look at this is like a 10-fold acceleration, like 20-fold acceleration. You can still see the, the part of the image that we're trying to do here. So in this case, this is an abdominal acquisition. You can still see the liver, the bowels here, even though we have this really high acceleration rate. And that is because we have these incoherent artifacts because we are sampling K-space in a radial fashion rather than a Cartesian fashion. And also extending this to dynamic imaging. So if we are doing this golden angle radial acquisition, so if we are using frames, so the golden angle trajectory doesn't repeat. So it's always a different spoke. So we have this what we call temporal incoherence, or different undersampling or different sampling pattern per time point. And so you're gonna get a video like this, right? Okay. All right, so, and a few years ago, as I mentioned before, so we did GRASP at that time. We were doing compressed sensing, and we were trying to enforce or exploit temporal sparsity or temporal compressibility. And with a very simple transformation, which is just the difference between frames. And these are like some results here. So this is showing dynamic contrast enhanced imaging in cervical cancer. So here's a tumor, and with a high temporal resolution. Sorry about that. And then, so the other one is motion resolve imaging in the abdominal area. So, and a few years later, so we actually started using supervised deep learning, that technique called movie nets. And so where we just use like a unit, a receiver unit, but we're trying to exploit space, time, and coil correlations. So we got slightly better results than GRASS, and the main difference was the reconstruction time, right? From minutes now, because it was iterative reconstruction, so you need to data consistency in each step. And by doing that with a neural network, we were able to reduce it's moving by itself. Good. So we were able to reduce, particularly the reconstruction time. So, but then the problem with supervised deep learning for dynamic MRI is that we don't have access to the ground truth. So it's impossible to get a dynamic MR image with simultaneous high spatial resolution, also high temporal resolution. So at the time, we use a GRASS as the reference to train this movie network. And it works well, so, but you still have some problems that were propagated from the GRASS reference. For example, if we look at the DCE MRI image there in the pelvic region, we're going to see some residual streaking artifacts, so residual aliasing artifacts. And so those were still propagated to this moving reconstruction. So that brings me to the topic today. Actually, can we see a way how we can self-supervise this reconstruction so we can remove this dependence on compressed sensing to train this neural network? And so for that, so after doing our golden angle radial acquisition, so maybe we can take a selfie and look back at this acquisition. And so if we look back at that, so we can see that actually we can extract some self-references directly from the data by using the fact that, or the property that golden angle acquisitions enable these flexible temporal solutions. For example, so since we acquire like hundreds of spokes, we can get maybe one or two anatomical references. These are gonna be with low temporal resolution, but they're gonna be fully sampled, no aliasing artifacts. And also, On the other hand, we can also go to really high temporal resolution, but with low spatial resolution or maybe with higher undersampling. So those can be extracted directly from the data. So the first one, the anatomical reference, will have, it's going to be fully sampled, but so no streaks, but it's not going to have any dynamic information. The other one will have the full temporal bandwidth, the full temporal resolution, but it's going to lose some features, some spatial features, okay? So we'll see how to combine them in order to self-supervise the reconstruction. And the other thing that we also know from compressed sensing is that these movies, these videos are very, very sparse, inherently sparse. So in compressed sensing, we are using this property to reconstruct. But what about if we actually use these to train the network? So we'll see how to use this cell sparsity and just using like a temporal TV loss term doing training rather than doing reconstruction. All right, so let me just walk you through some examples. Let's say that we acquire like 1,200 spokes. So it's a popular number of spokes. So and then if we're going to try to reconstruct like a 256 by 256 image, 400 spokes are enough to get like a fully sampled reference that is at the Nyquist rate. So we can get 3 of them. So these images, even though they are not going to have like the full temporal resolution, they are clean images, no streaks. So we can actually show these to the network. We can train the network. We can show that. So these are the images. So this is the kind of image quality that we want to get. On the other hand, temporal cell references now, if we say we acquire still the same data set, but now so we want to achieve 5-second temporal resolution. In this case, let's say that we need 21 spokes. All right, so we can now get like a high temporal resolution data. In this case with streaks, or we can in radial imaging we know that the center of K space is fully sampled, so we can maybe reconstruct like like a low resolution image, which will still have the full temporal resolution. Okay. And the last one, so we also know from compressed sensing that we iteratively do total variation, we eventually will get rid of all of these streaks. All right. So keep that in mind, and so let's talk now about the workflow and how we self-supervise selfie. So the input, we're going to operate in the image domain, so no data consistency in K space. So the input is going to be a multi-coil alias dynamic image, and then this is going to go through selfie, and then selfie will produce the output, which is going to be a coil combined dynamic image, and so we'll operate slice by slice. So in that way, so we don't need like so many patient data sets to train the network. All right, so then from the input, we can now get the anatomical cell reference, and this is just by averaging so frames from the input. For example, let's say that we have we're trying to reconstruct 256 by 256 images, and then we're using like 20 spokes per frame. So if we want to achieve 400 spokes, we need 20 frames. So we can average 20 frames, and that will give us the anatomical reference, which is going to be fully sampled. Okay. And then we also get the temporal cell reference. In this case, it's going to be a higher temporal resolution, but we'll have streaks or will be low resolution, low spatial resolution. And then the cell sparsity will be applied directly on the output. With that, we can form now this loss function, where the first term is going to be comparing like this, also the same kind of averaging operation that we did to compute the anatomical cell reference on the output. We'll compare that to the anatomical reference, and then also with the temporal reference, and we'll apply the temporal TV on the output during training. Okay. All right. So in terms of architecture, it's a residual units. The only thing that we do here is we apply separate spatial and temporal convolutional filters, so we can exploit spatial and temporal correlations separately. And we're doing this because, spatial and temporal correlations or spatial and temporal sparsity is very different. So that's why we do it separately. So in this particular case, our popular example, 256 by 256, that's the image matrix. So let's say 60 frames. And so in this case, we have 8 coils. And these are complex reconstruction, real and imaginary channels. So, and also the reconstruction here is complex. All right, so if we look here at the core of the layer, so we're gonna see, so the first kernel is doing the spatial correlations or the spatial convolutions. After that, we do the temporal convolutions, okay? And the same in the upper part, in the up sampling part, okay? All right. So let's take a look at now some results. So this is dynamic contrast enhanced MRI of cervical cancer. So temporary solution, 5 seconds, so 34 spokes per frame, 52 slices. So we only use 7 volunteers, actually in this case, to train this network, 2 for validation. And so the network didn't see any patients for training, so just volunteers. So anyway, we're showing a comparison between GRASP, which is a compressed sensing version, DCE MovieNet is a supervised learning using GRASP as a reference for training, and then SELFIE to the right, which is just using the self-supervised approach that we discussed a few minutes ago. So the main difference is, in GRASP, we still see these kind of residual streaking artifacts. Hopefully you're seeing them, yes. And also you're gonna see in the tumor part, because this is like a temporal total variation. Sometimes you can see these staircase artifacts. Those are fixed in part by MovieNet, but there are still some residual LSN artifacts. And SELFIE is doing much better instead of unstreaking the images. And also you had a very smooth contrast enhancement in the tumor region. Okay. And following Dan's suggestion, I also zoomed the tumor region because he was actually my mentor, right? All right, so this is, and just to show you that by doing this, actually we're not destroying the dynamics. So this is showing the signal intensity in that tumor region, comparing different reconstruction schemes. And as you can see here with SELFIE, we get like a more smooth contrast dynamics. Okay. This is another example. This is now doing free breathing dynamic contrast enhanced MRI in the liver. In this case, we have temporal resolution of 7 seconds. In this case, we use patients to train the network, so 20 patients for training, 6 for validation. So in GRASP, so it's good reconstruction. The only thing, there are some little artifacts. Also, you see motion in DCE MovieNet, so also similar to that. SELFIE is doing, I think, a little bit better in terms of artifact removal compared to the other two. And this is also showing here the results in terms of the contrast dynamics. And this is another example in the liver where there was more motion. And so where you can also see that SELFIE is getting a little bit better in terms of the streaking artifacts removal, and also in terms of like motion compensation. And this is also showing here, that again, this is the average signal in that region of interest. And since there was more motion here, you're gonna see more variations in GRASP, in MovieNet, and it's better compensated in SELFIE. Okay. All right. This is one last example also to show motion resolve imaging. In this case, with like 10 motion frames. It's showing a patient with liver metastasis. So usually MRI, so one of the main applications in cancer for liver MRI is to detect liver metastasis. we're doing a better job than CT on the detection of liver metastases. And so this will enable to do it during free breathing. Okay. All right. All right, to summarize, so if we take a selfie of these golden angle radial acquisitions, where we need to do it because there is no ground truth in order to supervise a reconstruction network. So we were using before compressed sensing results, but now if we do that, we take a selfie of golden angle radial acquisitions, we can actually exploit some acquisition and data properties. So we can extract these cell references, an anatomical reference and also a temporal reference. And also we can exploit this cell sparsity of the data during training in order to self-supervise the network training. And so it's starting to show promising performance, particularly for improved unstreaking, which is still a problem in radial imaging. And so, still a proof of concept, and we're gonna continue working on this direction, right? And I think the take-home message for the audience here is let's try to take a look at how we are acquiring the data and what are the properties of the data, and that probably can help us to self-supervise a network. I would like to acknowledge the SELFIE team, so in particular Melanie Schellenberg, she's the main architect of this work, and also Anthony and Vico, who supported the work. And thank you so much for your attention.
Hey, Ricardo, great stuff to see. I was actually thinking as you were talking about these sort of two different types of selfies, that in some ways you're kind of constraining your priors to be wrong in one direction and wrong in another direction, right? You know, accurate on anatomy, but not so accurate on time. So you'll have, you know, sort of blurring due to motion, or not so great in space, but really accurate in time. I wanted to know, kind of, is that a generalizable approach in the sense that, you know, can you be confident of the balance, or are you actually training the network to, you know, could it potentially incorporate both types of errors? And I guess I'm also just wondering in general if there's any relation to the previous talk where we, you know, there was this idea of kind of training with complementary degradation restoration functions in order to get better net performance. So it's a bit of a broad question, but any thoughts you have are welcome.
Sure. I think it's a great question, and it is related to a previous talk in the way that we don't have, in the cases where we don't have a ground truth, we need to find, like, for, let me put it this way, like maybe a partial ground truth, right? Yeah. So, and this is going to give us, so the solution can be projected, let's say, on the motion, the dynamic space first, and then it can also be projected on the spatial space. And so regarding the balance, so I think the network during training, so we are getting that balance by putting the two things together. Yeah. And not sure if it is optimal, but at least it's leading us to a way to self-supervise the reconstruction, and we are seeing at least slightly better performance than supervised learning.
Yeah. Thanks.
So I'll give you a quick online question.
Sure.
So it's from Abrar Istiak. I'm going to paraphrase this slightly, but how low of a number of spokes can you use to still get decent results with SELFIE, or kind of equivalent, I guess? What is the highest amount of acceleration it'll take?
Well, that depends on the application, right? In these particular cases, for dynamic contrast enhanced MRI, if you want to be like super accurate in terms of quantification, probably you will have to use more spokes. It's hard to say. Depends on the application, right? But we can go maybe to five spokes per frame. I would say probably that's like a minimum. In some cases, maybe we can go to one spoke per frame as long as we have a sufficiently long series. So Yeah, I think as long as we can at least get like one anatomical image fully sampled, probably we should be able to reconstruct. Yeah.
Hello, yeah, thanks for the great talk. I feel guilty asking this because I know you can't answer it in 30 seconds, but feel free to punt. So your compressive sensing result, yeah, I see what you mean. It wasn't quite as good. It didn't look bad to me, right? When you get around to taking the next step in image quality assessment and you objectively assess your results based on task performance, maybe there won't be a big difference, maybe between the compressive sensing images and learn.
Right.
At what point do you decide that it's worthwhile to assume the risk of using the learn method as opposed to just using the model-based method? So I know it's a general question, but I'd be interested to hear your thoughts about it.
It is a valid question. So yeah, image quality assessment is hard. In these particular cases, at least for dynamic contrast enhanced imaging, we try to quantify this and get actually the perfusion maps. And so we're using compressed sensing. We were seeing these streaking artifacts that were propagated to the quantitative images. So that we wanted to get rid of those. That was the main motivation, actually, to do this. Try to get rid of those streaking artifacts in the quantitative maps. And then for motion resolved imaging, probably it's more like we need to talk to radiologists and to see how do they feel about the image quality. That's the usual way we do it, and then we get to a little confidence. We say, oh, this is good or this is not good. So with compressed sensing, we got really good results. That's actually implemented in a lot of the clinical scanners. But now to take the next step, I think we're trying to get more into the weeds now and trying to get more quantitative data, and probably quantitative data will be the answer, right? So if we can actually improve the quantification of the data, so that will be the main motivation to go to new reconstruction techniques.
Great, thank you.
Very nice work. I also like the results of this grasp, actually, that the total variation minimization looks very good, very dynamically moving, as well as contrast changing and so on. I wonder, I don't have any question or particular comments, but I have a suggestion to look into, right? So if the object moves, deforms, that the pixel value changes abruptly in a step function, total variation works to model that. Right? If the contrast injected the organ, the contrast changes gradually. And then L2 norm minimization works for that kind of model. Somehow this learning-based one missed that abrupt change part so that organ doesn't move as dynamically as the total variation-based one, which is very good to model the pixel value change over time. So if you translate that into your work language, you might be able to find a better way to learn something from this chunk of this data set to train that, I wonder.
Okay, I think that's a great suggestion. So we will try to look into that, right? Yeah, but going back to the thing about motion, right? I think with deep learning, what we're seeing is that we can also do some kind of co-registration, and we're not losing the dynamics, right? So before, it was also risky to do this because that's kind of like temporal blurring. I think that's what you're referring to. If we're trying to introduce temporal blurring, so that can also, reduce the dynamics. But in this case, I think we are preserving the dynamics, but it's also doing some kind of co-registration.
I see.
Yeah.
Thanks, Ricardo.
Sure.